All right, well now let's do an example. Let's work out the uncertainty in the separation between the chlorine and the hydrogen atom in an HCl molecule using what we've just learned about the wave functions. All right, here, hang on and we'll get started. Very good. So, well, let's get started. So here's what we're trying to do. Imagine our hydrogen chloride molecule here with the chlorine and hydrogen joined together by a chemical bond. And remember, what we're really doing is we're approximating this bond as if it were a spring with some spring constant, kappa or K. Okay? And what I'd like to do now is to estimate the uncertainty in the position of the hydrogen atom. Here's the idea. If we make a graph of the separation between of wave function amplitude as a function of separation between the molecules, well, we know that it looks something like this. First, we have the potential. Well, let me try to sketch it in here. Like so. So here, the wave function describes the amplitude as a function of separation between the hydrogen and the chlorine atom. Okay? If you like, the width of this is telling us the uncertainty in the position of the hydrogen atom. Okay? And that's what we'd like to find. So we're not finding the separation between the chlorine and the hydrogen. We're finding the uncertainty in the hydrogen atom's position, more or less, or the uncertainty in the separation between the atoms. Well, let's go ahead and do it. So of course, we can do this because we know the wave function of the system, C 0 times e to the minus alpha x squared. Okay? Now, for the purposes of this problem, it's useful to define a new variable a, which is 1 over the square root of alpha. And that's just so that we can write our function this way. C times e to the minus alpha times x over a squared. Okay? In that case, a becomes something like the width of the function, because when x is equal to a, well, I'm sorry, I made this substitution so I don't have alpha anymore. When x is equal to a, then the amplitude of the wave function has dropped by one factor of e. Okay? So we're going to make this substitution, and then we're going to solve for a. All right? To do this, we'll substitute into this wave function into Schrodinger's equation and turn the crank. All right? So then we have we have minus h bar squared over 2m times the second derivative with respect to position of our wave function and this has to be equal to E minus U of x, the potential energy, which we can write as 1/2 m omega naught squared x squared times the wave function again. You know, I didn't leave myself enough room here, so I'm going to move this down to the next line. Okay? Looks a little messy, but this describes what we want to do. If we take the derivative on both sides, we take the derivative of the wave function on the left side, we can rewrite this and we'll end up with an expression for a. Okay? So The first thing to do is to take the second derivative with respect to position of the wave function. And I encourage you to do this. If you do this, you'll find that the answer can be written as 4x squared over a squared minus 2 over a squared. I'm sorry, in that first term it was a to the fourth in the denominator, times the wave function again, ce to the minus x over a squared. Okay? And when we substitute this into our equation, things will, well, we'll get the following. Okay? So now we'll have, sorry, we'll have the following. Okay? So we'll have minus h bar squared over 2m. And then we'll have 4x squared over a to the fourth minus 2 over a squared times the wave function. And on the other side, we have e minus 1/2 m omega naught squared x squared times the wave function. Notice the wave function cancels out here. That's telling us that this is a valid solution. This wave function is a valid solution to Schrodinger's equation, okay? And then it gives us an equation. We're left with an equation, which will be an equation for A, okay? Multiplying both sides by 2m over h bar squared, we get, excuse me, we'll get the following. 4 over a to the fourth x squared minus 2 over a squared here is equal to 2m over h bar squared times 1/2 m omega naught squared x squared minus e. Okay? So that's our equation that we have to solve. It still looks like a mess, right? It still looks complicated. But now we can appeal to something. If this equation is true, it has to be true for all values of x, right? And that means it has to be true, e.g., for x equals 0. When x equals 0, the equation simplifies quite a bit, all right? Then on the left side, we simply have minus 2 over a squared. And on the right-hand side, we have 2m over h bar squared times minus e. Okay? Really, what we've established is that the equation has to be true, that terms in each order on each side of the equation have to be the same. So the constant terms have to be the same, and the terms that vary like x squared have to be the same. By setting x equals 0, we see that the constant terms have to be the same. Okay? And then we can simplify this. Cancel out the negative sides, and we'll invert. We have a squared over 2 is equal to h bar squared m e over 2. I think I messed up the, yes, I messed that up. So, excuse me, let me rewrite that. We have h bar squared e over 2m, or a is equal to h bar times the, oh, I'm sorry, I left off some terms, didn't I? Excuse me. Give me a second, I'm just going to fix that. There we go. Now we're nearly done. We'll notice that the energy for the lowest state is equal to 1/2 h bar omega naught, and substitute that in. And we have a squared is equal to h bar squared over m times 1/2 h bar omega naught. And so finally, A is equal to the square root of 2 h bar over m omega naught. There we go. All right, at this point, we're ready to put in numbers. For the oscillator, m here is the reduced mass of the oscillator system, which we found was 0.97 times the atomic mass unit. Okay? While omega naught is 2 pi times the frequency of the absorption line, which is 8.66 times 10 to the 13. Okay? And then putting all these together, we can get an answer. Okay. And a moment with the calculator shows that this yields 1.66 times 10 to the minus 11 meters. Or, I think I put an extra 6 there. 1.6 times 10 to the minus 11 meters, or about 0.16 angstroms. Okay? So, what does that mean? It means just this, that the separation between the hydrogen atom and the chlorine atom in an HCl molecule isn't really fixed. Instead, it has an uncertainty of about 0.16 angstroms, on the order of a little more than 1/10 of an atomic diameter for hydrogen. Well, it's not that big, but it's not zero either. And we've just figured it out. Okay, let's stop this example here and stop this video.